Good morning, friends. Myself, Dr. Rohit Vaid, and I'm from Computer Engineering Department in Engineering College, Mulana. Today, I will represent the topic related to memory management, and we will discuss why this memory management is required in computer system, and what are different problems which we face when we will discuss memory management technique. And apart from this, this is the index which we should discuss. We will also study context switching and fragmentation. One by one we will discuss, and then we will continue. First of all, we will study the topic of memory management. And memory management, basically memory is an electronics device which is used to hold data and information, and the instruction which will execute on this data is stored in computer memory, and this memory is known as basically RAM. Whenever we will talk about the memory, then definitely we are talking about the main memory, that is RAM. RAM is, otherwise there are other memories also, like auxiliary memory, and sometime we will call that as a hard disk, CD-ROM, floppy disk, tape drive, all these are also memory, but when we will talk about the main memory, then we will talk about the RAM, or we can say the memory which is directly accessible by the CPU is known as main memory. Otherwise, the remaining memory which are used to back up the data are known as auxiliary memory or secondary memory. And today you will see we have a computer, and average, on and average, minimum 4 GB memory we have. The memory large in size, the less we will require to transfer the data from storage device, which is not as fast accessible as compared to RAM. So the storage device including hard disk, floppy, CD-ROM, tape, these are used for backup system, and the term auxiliary storage is used for these backup. And most computer have a memory hierarchy with a small amount of very fast memory and large amount of very slow memory. And we have to manage the memory. If you will see the memory hierarchy, then we have a very fast memory known as process registers, process cache memory. These are very fast memory, and there is also a medium size memory, that is RAM, flash drive, and there is a large size memory. If we will go downward to this hierarchy system, then we will see that the cost of memory per bit is reduced, but the access speed is also reduced. And if we will go upward in this structure, then we will see that cost of storing per bit is increased. So that's why the total cost will not increase. We will take the size as small as possible, so that we will maintain the cost also. If there is no cost issue, then definitely we will create the hard disk also for this material which is made for CPU register, but in that cost the overall cost of system will be increased. So that's why we will manage the computer memory. If you will see the next diagram, now the memory which is directly accessible by CPU is known as main memory, and the remaining auxiliary storage which we will use for backup medium is not directly accessible by CPU. There is a IO processor which is used to transfer the information between auxiliary storage and the CPU. And if we will take this auxiliary memory as processing, then overall cost in terms of access time will be increased. So there is a need to manage the memory, and when we will see about the memory, then we have a very small amount of very fast, expensive, volatile memory in number of bits, and we have a medium size memory which is 100 and 1000 of megabyte, and we have a disk storage which is very large as compared to this memory. and it is the job of operating system to coordinate how these memories are used. The primary motive of a computer system is to execute program, and these program along with the information they access should be in the main memory during execution. So according to memory management scheme, we will keep track of the status of memory. These are the responsibility of operating system. That is, we will keep track of computer memory locations, either it is allocated or free, and allocation and deallocation is also the responsibility of operating system whenever we will run the process execution. And the operating system will manage the memory in such a way that if a small amount of main memory is there and the program size is larger than this memory, then how to manage the memory so that the larger program is execute on low memory, means the size of memory is small but the size of process is greater as compared to memory. Even then operating system use the concept of virtual memory and manage in such a way that small memory will accommodate larger program. Then there is a fragmentation issue, we'll deal with that also, how we'll remove the fragmentation or otherwise how we will minimize the fragmentation. Then there is a proper utilization of main memory, and protection of memory given to one person is not interfere with the memory of other process. That protection we also required, so memory management is also required in that case. And sometime we will need to share the data or share the memory among two different process. So sharing, protection, proper utilization of main memory, removing of fragmentation, allocation, deallocation of memory, and keep tracking of the memory, either it is allocated or free. These are the responsibility of computer memory. And one by one we will do this topic. Now there are two addresses. Whenever we will write down the program and compile this program, then CPU generate dummy addresses, and the addresses are known as logical address. And whenever we will run this program in computer memory, then actual memory which is allocated to this process is known as physical address. So we need a mapping that will be used to convert this logical address into physical address, and this mapping is done by a hardware memory management unit. So logical address is the address which is generated by the CPU, and it is also known as virtual address. And logical address space can be defined as the size of the process. And similarly physical address, an address seen by the memory unit, that is one loaded into memory address register of the memory, is commonly known as physical address. Its physical address is also known as real address, where actual this program are running. So this set of all physical address corresponding to all logical address is known as physical address space. And you will see in next figure that CPU has generated a address that is 346, and we need a hardware unit that is known as a memory management unit, MMU. This will convert this address into physical address, and the base address is now called the relocation address. The address is sent to memory. For example, if the base address is 14,000, then the attempt by the user to address location 0 is dynamically relocated to location 14,000, and access to location 346 means we are actually accessing the location that is 14347. So this is basically done by the special unit that is known as memory management unit. And we have a base register and a limit register. This way we will convert this logical address into physical address. And suppose we have two different type of addresses, logical address in the range of 0 to max, and physical address that is in the range of base address plus 0 to base address plus max for a base value of R. So basically we will do this conversion, and the set of all logical address generated by the program is referred to as the logical address space, and the set of all physical address corresponding to these logical address is known as logical address space, that is physical address space. The runtime mapping from virtual to physical address is done by the memory management unit MMU, which is hardware device. MMU uses following mechanism to convert the virtual address to physical address. The value in the base register is added to every address generated by the user space, which is treated as the offset at the time it is sent to memory. For example, if the base address value is 10,000, then an attempt by the user to use the address location as 100 will be dynamically relocated to 10,100. So this is basically the mapping which is used. The user program deal with the virtual address, it never see the real physical address. So you will see in this figure memory allocation. These are the figure from ABC up to G. If you will see the first figure, then we will divide the memory basically into two parts. One part is permanently occupied by the operating system, and the remaining part is distributed to different process if multi-programming is there. And you will see first time the process A is coming to computer, and the processor is allocating the first part to operating system and the first next part to this process A. The next process enters the system B, the next process enters the system into C. Later on time you will see in figure D that A has complete its calculation or temporarily removed from the memory due to some IO event. So this location which is used by the process A is free now. Then later process D is entering into the system. We will allocate the space to D. Then B is removed from the system. Then A comes back to the system. This way, temporarily the process arrived into the system and later on left out from the system. And the process is known as swapping. And swapping is basically a mechanism in which a process can be swapped temporarily out of the main memory, and it can be moved to secondary storage disk and make that memory available to other process. At some later time, the system swap back the process from the secondary storage to main memory. If you will see the figure, then initially only process A is in memory, and here you will see that process P1 goes to IO wait. So instead of storing this process into main memory, we will swap out this memory temporarily to secondary storage device and move some other process which is waiting for memory into main memory from secondary storage to main memory, and the process is known as swap in. Later after some time P1 becomes back after completing its IO event and again move back into memory, and if there is a IO wait, then it will switch back to secondary storage again, and process P1 which has now completed its IO event again move back to main memory, and this way the process is known as swap in swap out, that is swapping. When swapping create multiple holes in memory, then it is known as fragmentation. We will study this topic later, but now from this time these are the technique which is used for memory management scheme. The first one is continuous allocation, other one is non-continuous allocation. And in case of continuous allocation, there are two schemes. One is single allocation and other one is multiple partitioning. In multiple partitioning, we have fixed partitioning and dynamic partitioning. And in case of non-continuous memory management scheme, we have paging and segmentation. And if you will see the continuous memory allocation scheme, in this scheme, memory management scheme, each program occupies a single continuous block of storage location, that is set of memory location with consecutive address. You will see. And in case of non-continuous memory allocation scheme, we have a memory. We will save this memory not at the same place, means consecutively memory is not allocated. We will allocate the memory into parts, and these parts are scattered in the main memory. There is no need to successively store all the parts of program into same location, consecutive location. So if you will see continuous memory allocation, In this scheme, each program occupies a single continuous block of storage location, that is set of memory location with consecutive address. And a single continuous memory management scheme is the simplest scheme used in earliest generation of computer system. In this scheme, you will see there are two type of scheme. One is single continuous memory management scheme. The main memory is divided into two parts. One is permanently occupied by the operating system and other one is occupied by the application programs. And the advantage of this scheme is that it is very simple to implement, easy to manage and design. In a single continuous memory management scheme, once a process is loaded, it is given full processor time and no other process will interrupt it. And there are some disadvantages also with this scheme. The waste of memory space due to unused memory, as the process is unlikely to use all the available memory space. Either it will require the small amount, but we will allocate the entire space to this process. And the other one is this CPU remains idle, waiting for the disk to load the binary image into main memory. It can't be executed if the program is too large to fit in the entire available main memory space. It doesn't support multi-programming, so we'll need the multiple partitioning scheme. And in multiple partitioning scheme, we will divide the memory into more than two parts. One part is permanently given to operating system, where operating system is loaded, and other part is divided into number of part, and each part is used for different process, and we will track either the part is allocated or free. And there are two type of scheme in this category. One is fixed partitioning memory management scheme. In this memory management scheme, the memory is divided into several fixed size partition, and the size of each partition is decided at the time of memory distribution, and the number of partition determines the degree of multi-programming, that is maximum number of process in memory. These partition made up the time of system generation and remain fixed after that. And there are advantage of this scheme. If you will see in figure, we have divided the memory into fixed partition of 8 MB each, and one partition, the first partition is basically allocated to operating system, and the remaining partitions are used for user process. This is simple to implement and easy to manage this scheme, but the disadvantage is that if some process needs only 2 MB of memory, but we have allocated this as 8 MB memory, so 6 MB memory is not used for other work. So this process is known as internal fragmentation. We have two fragmentation. One is internal fragmentation and other one is external fragmentation. We will discuss this. And in case of dynamic partition scheme, both of these problem can be lessened, which are disadvantage of fixed partitioning scheme. In this scheme, we will use unequal size partition. That is, if you will see in this example, program is as large as 16 MB cannot accommodate. Means if we have a 2 MB of process, we will store this into first partition and allocate only 2 MB space. Now the second process enters in this system, it is 4 MB of memory, we will allocate 4 MB to this process. Any process enters into the system, will allocate only the part required to this process. But if you will see, these are the differences between fixed partition and unequal size partition. There is advantage of unequal partition, that is simple to implement, easy to manage, and there are disadvantages are also there. The scheme also suffer from internal fragmentation. Suppose process enters the system, leave the system, and you will see the image after some time. If you will see these figure, the process 1 enters the system, it required 20 MB of space, we will allocate 20 MB to this process from the remaining 56 MB, and we have now remaining 36 MB of space which are used for other process. Now one more process enters the system which required only 14 MB of space, we will allocate 14 MB from this 36 MB space, will now required 22 MB free space. Now the process 3 enters into the system which required 18 MB of space. We will allocate this space to this process, and we will only remaining 4 MB of space which is unused. Now process 2 complete its execution and move out to the system. Here in this case, it is in the stage of waiting for some IO event. So we will swap out this process from the memory, and we have now 14 MB space which is used by this process is free space. Now at later time in figure F, process 4 enters into the system which only require 8 MB of memory space. We will allocate this space from 14 MB to this process, and we have remaining 6 MB of space here which is unused. Now process 1 moves out the system, that is swap out due to some reason, and now process 2 again brought into the system, and will allocate from 20 MB to this 14 MB space required to process 2, and we have now 6 MB process space which is unused. Now you will see, if one process enters into the system, for example, if we will read, we have 6 MB of unused space at one place, 6 MB at another place, and 4 MB space at other place. So we have a chunk of small holes in our memory which are unused. Total we have 6 plus 6 plus 4, 16 MB space which is unused. Now if there is some process which required 9 MB of space, we have space, but that space is not continuously available to us. So we have a external fragmentation here. Means space is there, but we can't allocate the space to process because the space is not at a continuous location. So the process is known as external fragmentation. And there are two kinds of fragmentation. One is internal fragmentation, other one is external fragmentation. You will see the example of internal fragmentation. In case of internal fragmentation, it is a problem that occurs when the process is allocated to a memory block whose size is more than the size of that process, and due to which some part of the memory is left unused. Thus, the space wasted inside the allocated memory block is due to the restriction of the allowed size of the allocation, and this scheme is known as internal fragmentation. If you will see the diagram, then the difference between the memory allocated and required space for memory by the process is called internal fragmentation. Our memory is divided into two parts, 200 and 200, and the process first occupies only 105 of MB space. 95 MB of space is unused, and this is known as internal fragmentation. And in second process we only need 165 MB of space, but because we have a fixed partition, so 35 space is unused. So both of these are known as internal fragmentation. You will see the example of external fragmentation. When the memory space in this system can easily satisfy the requirement of the process, but this available memory space is not continuous, so it can't be utilized further, then the problem is referred to as external fragmentation. The figure shown the external fragmentation. Suppose we want to allocate memory to a process of size 8 MB, and as in the above diagram we can see that there is enough space, that is 9 MB space we have a free, and still we can't give this space to our process. Means 6 MB is one part, 1 MB is other part, and 2 MB is other part. So we have 3 parts available. If these are continuously, then we will allocate, but due to the restriction in continuous memory allocation, we can't allocate these process to some process. So the process is known as external fragmentation. We have a placement algorithm also, but before this we will see the difference. That is, internal fragmentation occurs when the memory block of fixed size are allocated to the process, and external fragmentation occurs when the memory blocks of variable size are allocated to the process dynamically. And this type of fragmentation, internal fragmentation, in case of internal fragmentation, this is mainly occurs when the fixed size partition is assigned to process whose size is less than the size of the partition, due to which the rest of the space in the partition become unused. And in case of external fragmentation, when the memory space in the system can easily satisfy the requirement of the process, but this available memory space is non-continuous, so it can't be utilized further. And we have a placement algorithm also, that is 4 kind of placement algorithm. One is best fit, one is first fit, one is next fit, and one is worst fit. In case of best fit, you will see this diagram. We have a placement algorithm. Suppose we have a 6 MB of memory which we want to allocate. In case of first fit, the first flip block which is used accommodate this process will allocate from this place, that is first fit is 6 MB is allocated in this partition. From the 12 MB of space, 6 MB is used, 6 MB is fit. And in case of best fit, we will select that particular algorithm where wastage is minimum. And in case of next fit, we will allocate this space